Good morning and welcome to Troubleshooting Cable Networks, Understanding Ingress Impairments. This webcast is being sponsored by VeEX and by Apogis and is being hosted by CED. My name is Brian Santo. I'm the editor of CED and I'll be the moderator of today's webcast. With us today are Brady Volpe of the eponymous firm, Cyril Morel, CEO of VeEX, and Danielle Babot, Vice President, Business Development, Broadband Networks at Apogis. Their bios are available right there at a button on the bottom of your screen. Suffice to say now that these three have an extraordinary amount of combined experience combating ingress and other network impairments. Before we proceed, I want to remind our listeners that there will be a question and answer period at the end of the presentations. You'll be able to enter a question at any time during the presentation. There's a window on the left side of your screen. You just type in your question and click Submit, and we'll have it for the Q&A portion of our webcast later. If anyone wants to review this webcast, or if you want to invite anyone else to hear it, this presentation, complete with audio and slides, will be archived and accessible shortly from the CED website at cedmagazine.com. For decades, even after delivery networks were upgraded to become fully two-way, service to residential customers was largely about downstream transmission. That's changing and fairly rapidly, and that makes it even more important to make sure cable networks are properly maintained for more upstream communication. Our speakers today will talk about how to prepare for that. To start the discussion, I'm going to turn the microphone over to Brady Volpe. Brady?
Thank you, Brian. Hi, I am Brady Volpe. It is the Volpe firm. Brian, I think you had a different company there, but I am here to talk about transmission line theory and ingress with leaving out all the complex math that goes along with that. So for some housekeeping, we'll briefly look over the agenda. I'm up first talking on transmission line theory and impact of ingress on cable services like DOCSIS and video. Following me will be Cyril and Danielle, and they'll be covering the different ingress monitoring methods, principal causes of ingress, and identifying the potential operational impacts related to ingress repairs. We'll hold the Q&A at the end of the presentation. So a little bit on transmission line theory. As an RF signal propagates down a coax cable, we can look at each section of a coax cable and break it down into small lumped circuit elements. And we look at each section of the coax cable sort of as an inductor and capacitor. It's sort of how we can model a coax cable. And we call this a lossless model, which is the equivalent of a circuit transmission line as the inductors and capacitors. From this, we can focus on the two most important terms that characterize a coax cable, which are the velocity of a signal, also called the velocity of propagation, and the characteristic impedance, which is 75 ohms in the cable industry. For now, we're not worried about velocity of propagation. What is most important is the impedance. The cable industry, we know that all of our source components, transmitters, receivers, RF amplifiers, passive components, they have a characteristic impedance of 75 ohms. In order to get the maximum transfer of power into a coax cable, it's absolutely essential that the coax cable has a matching impedance of 75 ohms. If the impedance of the coax cable is not 75 ohms, or if the impedance of the devices, the transmitters, receivers, amplifiers, etc., are also not 75 ohms, then we're going to get reflections. And some of the power that we're trying to put into the coax cable is going to be reflected back, and we will not have maximum transfer of that power into the coax. So let me try to explain this concept without using math. So imagine if you have a water hose and you have a bucket of water, and then you want to try to pour that water from the bucket into the opening of the water hose. So you tilt the bucket and you start pouring that water into the hose. some of the water is going to go into the hose, but a lot of that water is going to splash out and be reflected by the hose back onto you, and you're going to get kind of wet doing this. So that's kind of the impedance mismatch between the water pouring in the hose being reflected back and onto you. Now, consider the same example where you put a funnel into the opening of the hose. Now you tilt the bucket into the funnel, and a lot more of the water is going to go into the hose, and a lot less of that water is going to be reflected back onto you, so you don't get as wet. Now you have a more efficient transfer of the water into the hose and a much more efficient system. So the final result has created an impedance match, and your system is much more efficient. So this is why impedance matching is very, very important in transferring energy from one system to another, in particularly coax and transmission line theory. So moving on to egress and ingress. Ingress is when you have signals leaking in to the HFC plant, and egress is when those signals leak out. Now, from my personal experience, I'm much more worried about ingress because those impact DOCSIS services and video services. If you look at the FCC, airlines, a lot of other radio stations and stuff, they care a lot more about egress because those signals leak out and impact the communication systems that they're using. So taking what we learned from the previous slide, we can start to look at how impedance mismatches can create an opportunity for ingress and egress and impact our systems. So oftentimes the shielding integrity of a coax cable will be compromised. And this can happen when, say, a squirrel chews on the mainline coaxial cable, or that coax gets dented or crimped for some reason. If there's a microfracture in the coax, which occurs when the actual hardline coax gets broken. Anytime this happens to the coax, when the outside shielding is compromised, we end up with an impedance mismatch. This impedance mismatch represents the opportunity for signals to leak into the coax, which is ingress, as well as signals to leak out of the coax, which is egress. Other types of impairments can happen where you have signal mismatches, such as bad grounding, a broken connector, a loose or corroded center seizure screw. These are all examples where you would have an impedance mismatch in the HFC network. Lost signal integrity or connectors that are broken or disconnected or have corrosion on them are all places where ingress can be present in a plant. Now, depending on if these ingress signals are in the downstream path or the upstream path will determine what services are affected. So, if it's on a downstream, it's going to impact video signals on the downstream. If it's on the upstream, it's going to impact your DOCSIS upstream coming from the cable modem. What we were talking about, if you've not experienced LTE and 3G interference, it is something that is popping up. It is causing problem on our downstream in the 700 megahertz to 800 megahertz band. And so if you do find impairments like macro blocking or toweling issues or even video channels being completely knocked out on the downstream, take a look for LTE interference under the DOCSIS channels, or under the video QAM channels, or perhaps even you'll see it riding on top of those channels. Starting at channel 52, going up to channel 69, or even perhaps above those. So, what does upstream ingress look like? We see a pretty noisy upstream channel in this slide, and the upstream DOCSIS channel should be very visible here as that is sort of the highest hump, clearly makeable haystack in the center of the channel. There's also a vertical red marker right through the center of the DOCSIS channel that you should be able to see. Now, what I really like about this particular upstream capture is that it is in max hold right now. So the green line you see is showing relatively high levels of noise, but this noise is predominantly burst noise or impulse noise. So it's not consistently there. When the max hold is turned off, this return path looks pretty clean. So clean, in fact, the tech did not believe there were any issues with the upstream until it was put in max hold. And you can see the blue line underneath the green trace, which really shows what that typical upstream looks like, which is, you know, the real problem there, that if you don't know to put the spectrum analyzer into max hold, you'll miss it. Now, I use dynamic modulation profiles when I configure CMTSs, which means that in noisy environments, the upstream modulation for data traffic from the cable modems will automatically switch from 64 QAM down to 16 QAM and even down to QPSK in really noisy environments. But in this particular case, the impulse noise was so random and so intermittent that even with dynamic modulation, it just was not kicking in enough. So we were seeing a lot of uncorrectable code word errors, and voice over IP was really being impacted. So I had to manually force this modulation profile down to QPSK before the system would reliably work, the DOCSIS system for data traffic. Now, the source of the ingress turned out to be multiple problems. There was one drop cable that had a splitter that had been at some point fried by a lightning strike by a nearby tree. And this was letting a lot of ingress into the upstream. There was also a 400-foot span of hardline cable. And this span had a number of microfractures in it. And these microfractures are just small radial cracks the whole way around the coax cable, the hardline coax cable, which are causing impedance mismatches at each one of these fractures that lets signals in and lets signals out. In addition to that, we found a number of RF amplifiers that didn't have their covers tightened down. They had loose center seizure screws, corroded center seizure screws. Each one of these points was a place where we had impedance mismatches. We had ingress getting in. And so, you know, not every one was the main cause, but each one was letting a little bit of impulse noise in at different frequencies. And so it took us about a week to find all these different issues, but each one was a contributor. Now the upstream's back to 64 QAM, and the SNRs from the cable modems are back up to around 36 dB. But this was a very, very painful process to track everything down. So you know, the impacts of ingress and return, we've probably all seen at one time or another if we work in the cable industry. And we see it's robotic voice for voice over IP, data loss for cable modems, correctable, uncorrectable code word errors, which are the worst for cable modems. Maybe the modems won't come on at all. We'll have T3, T4 timeouts. And downstream with, you know, poor video, macro blocking, pictures freezing up, subscribers complaining like crazy, which means we have, you know, a lot of truck rolls, maybe truck rolls going to subscribers to try to make them happy and resolve their issues, and then just a continuous truck roll. Like I said, you know, we spent a week going back and forth trying to find all the problems that were out in the field. So it's very problematic and something that is not easily found at all. So to wrap things up, you know, ingress identification is just not something easy to do. It's normally many things out there that cause it. And cable leakage does not necessarily mean that you have cable ingress or necessarily egress. So this will be covered later on in presentations after mine. When you eliminate ingress, it's going to be back. So it is important that you have some sort of preventative maintenance program out there that you're, you know, continually staying on top of this so it doesn't get to the point where it is as bad as the previous slide that I showed. And having the correct tools to be able to identify it and go out and find it and track it down are really quite critical in a network. And also, you know, something else available is like proactive network maintenance tools to help you identify it are also extremely, extremely helpful. So that concludes my portion of the presentation. I want to thank you very much. Next up is Cyril Morel. He's going to talk about some ingress monitoring methods. So thank you, and Cyril, take it away.
Thank you, Brady. I think actually the problem that we had this morning proved the point that you do need to monitor your communication system. If not, you do have problems, and they are very difficult to solve. So when you look at ingress, the first method that we're going to talk about is actually the ability for a system to get drop in and monitor your return to detect this ingress. One of the things that is very important is actually there's quite a few systems out there from different vendors, but it's important to have a system that can allow you to monitor the ingress, what we call constantly, and provide the alarms associated with the ingress, but also allow you, without disturbing the monitoring, to do on-demand tests when you try to go and hunt and repair the ingress, like Brady explained, that you need to fix it, but it's going to come back. So it's very important to have a system that allow you to have the probes mounted that are available for on-demand and constant monitoring. Now, if you want to go to the next step, it's easy to just drop a system and think that the system is going to live by itself. And then you deploy the system, you invest a lot into deploying the system, but it's not get used. And it's not get used for a couple of reasons. One of them being that actually there is no integration of the system. It's very important that as you detect the ingress is reported back to your system, integrated into your dispatch system, and that creates tickets automatically for your OSP technician to go fix this ingress. And that brings us to the second part of the problem, is now that you have a technician out there, he needs to be able to sectionalize the ingress. So one of the things that you can do, and has been used for years, is using the sweep. The problem with the sweep is both on the return and the forward, is the spectrum is getting crowded. And we have nobody that has yet made a decision on where the spectrum is going to go. Are we going to increase it to higher frequency? Are we going to move it above 1 gigahertz? So far, it's very difficult to sweep because you really have very limited insertion points. And that creates a problem. So one of the ways that you can do is actually, instead of sweeping, is use the transmitter that will allow you to transmit a known signal similar to the cable modem, and have your monitoring system to analyze this signal that you're injecting, and you bringing the MER and BER analysis that you normally do on the downstream into your return path. And that really allows you to see if you have problem with ingress and sectionalize them in your network once you have detected that the ingress was there. To add to the puzzle, one of the things that is very important is you need to picture a technician at 2 a.m. that is trying to solve an ingress problem to make sure that the next morning everybody is going to be happy with their DOCSIS and their download and their upload. Well, often it's very difficult to have somebody in the head end to be reachable at 2 a.m. in the morning. And what you want to do, you want to make sure that your solution allows you the ability to have a field view into your meter when you generate this signal. Additionally, as you sectionalize the problem, one of the things that you want to see is you want to see that actually if the problem is coming further into the network or at the point that you are. And one of the ways to do that is actually with a tool that allows you to do what we call dual spectrum view. That will allow you to see what the monitoring system sees in the head end and also what you see locally. So if you go to the first node point that you're going to test or the first amp, then you can see that actually locally you don't see any problems, but actually the head end still sees the problem. So that allows you to go back towards the head end and go to each point and so on until you find the source of the problem. And to really make your system complete, you need to think about being able to see everything everywhere. We are in a world where everybody now has a smartphone or a tablet without making any brain assumption. And it's very important that actually you can see all this information in real time from any devices that you have, so you really become efficient at fixing the problem. This is one of the solutions that we are proud to support and to commercialize. And actually, I'm going to pass the hand now to Daniel, that's going to show you not really another solution, but a solution that is complementary to this one and works in conjunction with the one that I just presented. Daniel, take it away.
Yes. Thank you, Cyril. So we came up with a different method, which I think is complementary to the method Cyril just explained. But before going into the architecture, let me explain a little story. A few years ago, I was a tech op director in a cable company in Canada. In 1995, we launched the high-speed cable modem service there with using a Zenith cable modem. Was basically a 500 kilobit per second cable modem. And one of the first issue we did encounter is, obviously there were cable ingress when we started into that business. And basically the only troubleshooting method at that point in time was using, and probably a few of you guys will smile, you probably already all done this, using a CB and a spectrum analyzer. So you have a guy driving, a technician in the field, and you have somebody at the end with a spectrum analyzer and looking for that, 27 megahertz carrier coming in, going out, at different input levels. So you may recall that this troubleshooting method was very long and tedious process. It could take hours, if not days, to locate a source of ingress. So just coming back, so we came up with a different method where we are using a continuously transmitting device called the ITX1 in the upper left corner of the slide, and we use that with an ARD4 module, which is kind of a computer. The two devices are installed in a truck. While the technicians are doing, their regular install service call, we're continuously transmitting that carrier in the upstream band. And at the ADAN location, if you look on the upper left right of the slide, you have a receiver that is tuned to that upstream carrier and basically listening for that carrier. So if we are detecting the transmitted carrier, you know that you have an ingress entry point, basically where the vehicle is located. Once the IRX1 has detected that, we're pushing back the information to the CPAP server, and we have, a full dispatch application running so you can send your tech out. So when your tech is out, we require any web-enabled device. In the slide, we're using a cell phone. And the purpose of the cell phone is basically to get a readout of the ingress level that is being seen by the IRX1. So assuming on Monday we locate an ingress point, next day we're sending the guy there equipped with the equipment. He just needs a cell phone, just drive to the ingress location point that was identified on a digital map set and basically start doing his work, and he will see the ingress level on his cell phone. So that's the eye-level concept. So the system is fully automated. So we're recording while the technicians are driving out to do their installs, their work order. We're continuously broadcasting that signal. Why? Because as Brady explained previously, sometimes the ingress signal could be of an intermittent nature. Like you could have a guy driving with a van using a CB and using very high power amplifier. It could saturate the return optical receiver. The problem is you're recording this But the problem is the guy is gone. He's driven off your plant. You send your technician there, and the ingress is gone. But you still have that crack in that cable. So continuously transmitting that signal and assuming you have enough penetration of those equipment will ensure you that you will detect those cracks before any of those intermittent issues pop up. The technology uses GPS receiver. So once we have located an ingress event, we have the ability to position it exactly on a digital map set, which facilitates the location of the ingress source. We only need one person to fix the problem. The ingress source are fixed in minutes versus hours, using the different methods out there. And now ingress monitoring is an hands-off operation. The transmitter module operates on a fixed frequency. We're using a robust digital modulation technique because at 6.78 megahertz, you guys know if you look at a spectrum analyzer, there's a lot of impulse noise present there and all kinds of undesirable RF product. The power level we're using on the device is compliant with FCC regulation related to radiated field at that frequency, and again, there's no user intervention to operate. It's very cost effective. We can locate ingress within a precision of plus or minus 2.5 meters. We can track multiple ITX-equipped vehicle. We could detect up to 100 events per second per IRX1. If you have that many events per second, you're in real problem. We have a 32 RF port on the back, and if you're using 4-to-1 upstream node combining, one receiver can do up to 128 upstream nodes. On the application side, we're using what we call a RIM-based. It's a web-based application. It requires a web browser-enabled device. Could be a cell, an iPad, whatever. You enter username, password. You select the proper ITX in use, and we will get the RX1 at the end. We'll get that level from that IRX1 in DBMV, and we also have portable ITX version for MDU and backlot operation. Okay, we'll look real fast at the different upstream ingress causes. These are actual ingress events that we went on and fixed with the local technician and took pictures. So we have visible scroll through on this one. We have a cracked trunk cable. I think everybody can agree that from the ground, this would be extremely difficult to locate such an impairment. We also have loose fitting, corroded drop cable. We also have rat shoe. We can have loose termination causing some issues. And one important fact, Brady mentioned this a little earlier in his presentation. Why is it important to have, an ingress monitoring solution? You probably heard all folks say that, if you do a good job cleaning up your leakage in the forepath, you should be doing a good job ingress-wise on the upstream plant. That is not true, and we have made some, testing a few years ago using lab-grade test equipment, a technology very similar that we have right now, but at that point in time, we use lab-grade equipment. So what we did, we've driven out basically around 25 different cable system of different size, could be rural up to high-density urban area. It was about 18,000 miles of two-way cable plant. So the objective of that drive out was to locate all ingress and egress events. So during that drive out, we collected a total of over 16,000 events. An event could be strictly a leak, strictly an ingress event, or a co-located leakage and ingress event. So if we look at the pie chart, we have just over 7,600 strictly leakage events, which represent 47% of the total events. I also have 11% of co-located leakage and ingress, just over 1,800. So if we fix everything up strictly from a leakage standpoint, the best you will do is fix 47 plus 11, which makes 58%, leaving you with 42% of unattended ingress events. So it's very important that you not only have a sound, good leakage, maintenance program, but you also need a good ingress monitoring and repair program. What are the positive operational impact of fixing ingress? This is one customer tried our equipment, during a trial, and we can see the different ingress event. As you can see, there's a lot of them, and different intensity. So we have a color scheme where you have the triangles. They go larger in size, so that tells you have higher ingress levels. So a triangle is strictly ingress event, and the square are co-located leakage and ingress event. So as an operator, we've taken out the leakage off of this for clarity purposes. So as an operator, you want to, make sure you go out to the bigger squares, because with one truck roll, you will repair two different events. So during that period, which started in January 2012, they measured, service call they had a few months before this, and once we start using the technology and they were aggressively pursuing the repairs of these, they benefited from an 18% reduction in service calls. The reason why they were so aggressive, they are fighting an incumbent phone company very similar to Verizon, which delivers broadband cable service using fiber optic. The other positive impact was on the severely degraded modem hours. So there's two curves in there. One is the damaged modem hours, which is the the red line. Damaged modem hours will impact your high-speed cable modem, delivery. Not to a point where customers are going to be calling in, but it will, probably lower the transfer speed of your cable modem. The blue line is what we call severely degraded modem hours. These one are damages that are such that the customer is going to start calling in. It's either internet service is intermittent or extremely slow to a point where they're going to call in and generate service call. So they enjoyed a 94% in severely degraded modem hours reduction. And on the damaged modem hour, the red line, they enjoyed an 87% reduction during those months. Another positive benefit of repairing ingress sources is the impact on average upstream signal-to-noise ratio. This was another system where we were trialing our technology, so we can see the pre and post repair impact on signal-to-noise. So the blue marker is signal-to-noise before we repaired the ingress source, and the red cylinder is after we repaired the ingress sources. So in the lower band portion of the upstream path, we basically got a 1 dB improvement in signal-to-noise ratio. Higher in the band, we got half dB. May not be much, but you rather have these in your pocket. So to conclude, our methodology is more acts as a preventive than reactive monitoring method. It's very cost effective. It's scalable depending on the upstream combining scenario you may look at. Automated. There's no user intervention during the monitoring process. We can reduce your ingress locate time, accelerate repair, reduce your cellular damage modem hours, increase your upstream signal-to-noise ratio upon repair of the ingress sources. So there's a lot of positive advantage monitoring, but the benefit is really from fixing those, and we have the tool that will accelerate that process. So I'd like to thank everybody, and we would like to see you guys at the Cable Tech Expo, where we're going to launch our digital leakage monitoring system. Thank you.
Thanks, Danielle. Thanks, Zero. Brady. We'll have a little bit of time for questions and answers. If anybody wants to, has any questions for the speakers today, there should be a window for you to type those in. If there are questions left unanswered, the panelists will get a list of those questions with your contact info, and they'll be able to get back to you within a few business days. We'll try to answer as many questions as we can in the time allotted today. Earlier, we got a question in, Brady, that about the characteristics of LTE spectrum and the possible noise problems associated with that. I'd like to see if I could just ask you to kind of revisit the question and your answer for the folks at large here.
Yeah, so what exactly was the question? It was the one on what the frequencies are?
Yeah, exactly.
Yeah, so I mean the dominant LTE frequencies in North America start around 700 megahertz, channel 52, and go up to the upper end of the 700 megahertz band, even a little bit into the 800 megahertz band around channel 69. So for LTE, that's predominantly where the frequencies are. There are some frequency allocations just into the lower end of the 800 megahertz band, but right now it's the channel 52 to channel 69 where you're going to see most of the LTE interference. And if you've seen it, there are places where I've seen on spectrum analyzers where it's severe enough where you can actually see the LTE riding on top of the DOCSIS or the QAM channel, but oftentimes the QAM channel is going to be dominant, so the LTE interference, you're not actually going to see it. It's going to be underneath. It's going to be running under the QAM channel. So the real challenge is how do you see that LTE? One way you can do it is temporarily turn off the QAM channel, which is sort of invasive because all the subscribers are going to lose video at that point, but maybe that's what you have to do in order to see if you have interference there. The other way is there are some tools out there that let you look under a QAM, an active QAM channel, and see what type of interference are underneath that.
Very good, thanks.
If I may add, Brian, this is Danielle. probably a lot of you guys been following the FCC meetings on the 600 megahertz band auction that's going to happen in 2014. So in the slide we did show there's going to be basically around an additional 100 megahertz of LTE spectrum that's going to be allocated. So the problem is just going to increase.
Yeah, I think we have to assume that there's going to be, and there's a lot of other wireless spectrum out there that's continuing to, as Danielle says, continuing to be auctioned. It's very valuable space, and there's more and more high-power wireless devices out there that we're going to see coming in and ingressing into our networks. But if we have those signals ingressing in and impacting our video channels, we also have to realize that we have frequencies that are egressing out of our cable networks, in which case that becomes, we're also probably impacting someone else's wireless space. So it is a two-way street. So the LTE folks are just as concerned with the signals that are egressing out of our cable networks and creating problems, interference problems with their LTE networks. So it's a problem for us. It's also a problem for them. So it's important that we tighten up our HFC networks to reduce the problems for really both parties.
Very good. This next question is probably for Danielle. We were talking about loading various vehicles with the equipment necessary to identify potential problems. The question is, if you're an installer, you're on, it's the equipment's in your truck, you're on your route, and you're doing installs. How does what's the process for actually addressing the impairments or potential impairments that you identify? I imagine the installer isn't going to be stopping his truck and every time he detects something, a potential problem. How exactly do you arrange to do the mapping and then actually go and address these problems in an efficient manner?
Yeah, there's a few assumptions that we have to take into account. Like we did for our leakage, a continuous CPAT, by the way, stands for continuous patrol. One of the assumptions is we need a specific percentage of the trucks equipped with the equipment. Assuming you comply to that, rule of thumb, the idea is since the guys are driving out doing their regular work, they will automatically record or transmit, I should say, that frequency. That frequency is going to be detected at the end. So there is some processing algorithm going on real time, recording this, positioning this on a digital map set. In the processing algorithm, we take into account, if two technicians have driven at the same ingress source point, we don't want to generate two work orders for this. So there's a lot of thought process that went into those algorithms. So whatever is inserted in the database, these are unique events. Obviously, when depending what the source or the problem is, obviously you need some transmission to relocate that source of ingress. So the next day, the technician will have its work order. He will drive out to a specific address. The transmitter needs to be on, and basically doing visual inspection. Remember that it will be plus or minus 2.5 meters from the source of ingress, so it's going to be fairly easy for him to locate the the source, and he's going to close his work order upon completion of repair. So it's kind of a two-step process where we let the guys monitor what's going on during the drive-out. We locate this on our CPAP database, and after that we go out with work orders and just close out the work process. So we're not doing any divide and conquer approach to locate the ingress. This has already been done in the post-processing, live post-processing of the database events.
Very good, thank you. I think all of our grandmothers probably at least once told us an ounce of prevention is worth a pound of cure. In a case where of ingress monitoring, this is definitely an ounce of prevention. I guess the question is, not everybody's grandmother is working in the finance department of your potential customers. Is there a clear justification for doing ingress monitoring in advance? What do you tell your customers, and what do they tell you after they've implemented these measures to get a sense of the worthwhileness of doing ingress monitoring?
Well, if I may intervene, basically, the cable industry is operating in a very competitive environment, and you need to provide continuity of service and provide good value on the service you provide to your cable subscriber. And I think that making sure that the plant is clean from egress or ingress standpoint is a very good method of providing the quality of service and the speed, especially the speed of service for the high-speed cable modem. We're going to be using even more efficient modulation technique in DOCSIS 3.1. So I think it's paramount that the plant we're deploying those services is clean from a downstream and upstream standpoint relative to shielding integrity.
Excellent. We have gone a little well over our allotted hour. I'd like to thank our presenters for being here today. And I'd like to thank all of you listening for your patience. Our panelists today were Brady Volpe of Volpe Firm, Cyril Morel, CEO of VeEX, and Daniel Babot, Vice President at Effigus. Gentlemen, thank you very much. I'm Brian Santo. I'm the editor of CED. Thank you all for joining us and for your patience today. Today's webcast was a presentation of CED and was sponsored by VeEX and Effigus. This presentation will be archived and will be accessible shortly from the CED website at cedmagazine.com. The URL is on your screens right now. Also, there's a button at the bottom of your screen that looks like a file folder. You can find a copy of today's PowerPoint presentation along with some supplementary materials. And that concludes our presentation.